Welcome to Mrs. Neller's notes for her pre-calculus class. These are the notes for section 5.6, day 1, entitled Modeling Harmonic Motion. And today we're just going to model simple harmonic motion and damped harmonic motion. And the reason we're talking about these types of real-world situations is because they use sine and cosine functions in order to model what happens in waves. So the first type of behavior that we're going to talk about is the periodic harmonic motion. And the periodic behavior means that it repeats over and over and over again. So it's cyclical or periodic. And that's what we see when we look at either a sine or a cosine curve. It's that wave. And you can see this in lots of different places. You can see it in the sun. You can see it in high tide and low tide. You can also see it in animal populations or in different situations where there's vibrating or oscillating parts. You can see this harmonic motion when you're dealing with springs and with sound and light waves and electronic current as well. Okay, so there's lots of real-world situations that have this periodic harmonic motion that they're using to model their behavior. Okay, so we're just going to focus on the sine and the cosine curves again because they have this repetitive motion to them. Okay, if we kept this graph going, it would again go up and down and up and down and up and down. And if you, just for example, take a look at a spring, if you had the starting position for a spring and then something acted on it to push it up, it would move up and then it would eventually, get so tight and reach its maximum compressedness, and then it would spring back down and it would go down to the starting position, but then it would go even lower and stretch out. And then once it's reached its maximum stretching capacity, then it would come back up and it might repeat over and over again where it compresses and then it stretches and compresses and stretches. Okay, so that is one way that we can use the sine function to model a real world situation. And since the mass returns to its original position over and over again, that's where we get this cycle or this cyclical period. Okay, so in this section, they might refer to the cycle more so than the actual period, but it's the same concept. Okay, when we were graphing the sine and the cosine curves, we referred to it as a period, but a cycle is one wave. Okay. All right, now we're going to see a couple different equations for these harmonic motion problems, and they're similar to what we've seen when we were graphing. We saw y equals a times the sine of k times x minus b, or y equals a times the cosine of k times x minus b. And they're basically using that same format, they're just tweaking it a little bit. Now this chart is also on your book on page 413, and I would make reference to it while you're working through the practice problems. But they still have an A for an amplitude, they still have the sine or the cosine, and then they change the values that come after that though. Instead of k times x minus b, they have w times t. Okay, so that w is a new variable, but it has the same effect as the k does. It's still that constant. Okay, so this w here, we're going to treat like the k value that we did in our other equations. So to find the period, we're still going to take 2 pi, but instead of dividing it by k, we're going to divide it by w. So that period then will find the time that it takes to go through one cycle or one period of the graph. And then if you reverse that, if you take the inverse of that period, you actually get your frequency. So if you do W divided by 2 pi, that tells you the number of cycles per unit of time. Okay, so those are the three new pieces of information that we're going to be seeing. And then they do, on this next page, tweak the equations just a little bit more, just another variety for them. They put a different variable in there. Okay, we still have our amplitude and we still have sine, but now we also have this 2 pi and then the v. Okay, so that v is just another way to represent the frequency. Okay, so let's take a look at some examples here. I believe we have 4 examples for how we can apply these new equations, and we'll see some other equations as well. Okay, but here we're going to talk about a vibrating spring, and it says that the displacement of a mass, so that would be this little boxy thing at the bottom here, suspended by a spring, so here's our spring, is modeled by this equation, or this function. We have y equals 10 times sine of 4 pi t. And y is going to be measured in inches, and t is in seconds. So they want us to take that equation, or that function, and they want us to find the amplitude, and the period, and the frequency. So if we look back at our chart here, the amplitude is going to be the number out front. The period is going to be 2 pi divided by whatever's in front of that t value. Okay, so our amplitude, since I'm squished for room here, maybe there's one on the other side. Other slide. There we go. Okay, so there's our function, and our amplitude is still going to be 10. In this case, it would be 10 inches. I think they said that, yep, y is measured in inches. Okay. Then they also want us to find the period. To find the period, we take 2 pi and we divide it by w. So again, that was the stuff in front of t, so that's going to be our 4 pi. Okay. So we'll have 2 pi divided by 4 pi. So there the pi's cancel and we reduce, so we get 1/2. And that would be half of a second. And then for our frequency, we're basically just going to take the inverse of this. We're going to flip-flop it around. So it would be w over 2 pi. So we'll have 4 pi over 2 pi. So that's going to be 2 cycles per second. Okay, so that means that for every second, there's going to be 2 cycles or 2 periods of this graph or this wave. And that should make sense because if it takes a half a second to do one period, then there should be 2 periods in a whole second. So for part B, when we sketch this, we can just sketch it by hand. Graph paper probably won't be too useful for these situations. Let's see, our amplitude was 10, so we're going up to 10, and then we're going down to -10. And it was a sine curve, so we're going to start at 0. And then after a half a second, we will complete one cycle. And if you wanted to do 2 cycles or 2 periods, you could put in the whole second. Okay, so at a quarter second, we'll be halfway. So we're going to go up, we're going to come back down, go down to -10, and then we're going to come back up. So I didn't draw that very evenly, but we could do the next cycle here. We're going to go up and come back down, and then down and back up. Okay, so again, when we're making these graphs, they're going to be a little rough. You could graph it on your calculator. I don't think you need to. The graphing calculator would just get you decimals to graph, but it would show you what it looked like at least. So there's a much nicer graph, much neater one that the book does. Okay, so that was just practicing the basics of the amplitude and then the period and the frequency and what these graphs will look like. Okay, so here we're setting up another situation for example 2. And this is where we're dealing with sound. And sound is produced by a regular vibration in air pressure from the normal pressure. If the pressure varies in simple harmonic motion, then a pure sound is produced. And the tone of the sound depends on the frequency, and the loudness depends on the amplitude. So that piece of information right there is going to come in handy for this next example, where they're going to talk about a tuba player. Here a tuba player plays the note E and sustains the sound for some time. For a pure E, the vibration and pressure from the normal air pressure is given by this equation. V of t equals 0.2 times the sine of 80 pi t. It says that V is measured in pounds per square inch and t is measured in seconds, so t is time. So they want us to find the amplitude, the period, and the frequency, just like we did on the previous example. Then we're going to sketch it, and then they have a couple more application questions here. If the tuba player increases the loudness of the note, how does the equation for V change? And if the player is playing the note incorrectly and it's a little flat, how does the equation for V change? Okay, so again, we want to remember that the tone depends on the frequency and loudness depends on amplitude. Okay, so the louder a sound is, the taller the graph is going to be. And the tone, the better the tone, the more frequent, I guess it would be, since tone and frequency are connected. Okay, so let's just take a look at A here, where we're going to find the amplitude and the period and the frequency. Again, it's a sine function. So our amplitude is still going to be that value out in front. So it will be 0.2. So we're going to go up to 0.2, and then we're going to go down to negative 0.2. The period, it's still going to be 2 pi divided by that W. And in this case, our W amount is all the stuff that's in front of the T, so that's 80 pi. So we'll have 2 pi over 80 pi. So that's going to be 1 over 40. Okay, so that means for every 1 second, there's going to be 40 cycles. Okay, so in order to complete one period or one cycle of this wave, it's going to be 1/40th of a second, actually. And then we still have to find our frequency. And remember, we basically flip-flop our period here. We'll have W over 2 pi. So that'll be 80 pi over 2 pi. So that's 40. Okay, and again, this would be cycles per second. Which again makes sense. If it takes 1/40th of a second to complete one cycle, then there should be 40 cycles in a whole second. So we want to think about that when we're drawing our graph. I don't want to draw a graph where we go out all the way to 1 second and then I have to draw 40 of these little sine curves all smushed together. So I'm going to do a little bit less time when I do my sketch here for my graph. I'm still going to go up to zero point 0.2, and I can still go down to negative zero point 0.2. Okay, but I don't want to do a whole second, because if I did a whole second, I'd have to draw 40 of those graphs. If I did a half a second, I'd have to draw 20 of them. And it's probably going to be a lot, but even if I did a fourth of a second, I still have to draw 10 of those cycles. Okay, so let's see here. If I did just one cycle, I would start at 0, and then I would go up to zero point 0.2, I'm going to come back down to 0, then go down to negative zero point 0.2, and then back up. Okay, so there's one cycle. And then I would have to repeat that 9 more times. So 2, 3, 4, 5, 6, 7, 8, 9. Oh, squeeze it in 10. I got shorter here as I kept going. Okay, pretend those go up. Pretend they all go to zero point 0.2 and then all the way to negative zero point 0.2 as well. Okay, so again, when you're doing these by hand, the graphs get a little messy. I think I have a nicer graph in here that we can take a look at. Okay, and here the book is going all the way to a half a second, so there's 20 of those cycles in there. And see how smooshed together they are? So that's what you might see on your calculator if you graphed that in your calculator. But graphing it by hand, you can adjust how much you want to draw and graph. Okay, now for those application problems. If the tuba player increases the loudness, I'm going to go back up here for just a moment. If the tuba player increases the loudness, how is that going to affect our graph and our equation? Okay, how does the equation for V change? Well, if it gets louder, then that means that we're going to increase our amplitude. So our amplitude was 0 0.2. So that means our new amplitude would have to be greater than 0 0.2. That's basically the conclusion they want us to make there. Our amplitude would have to increase. And then for part D, it says if the player is playing the note incorrectly and it's a little flat, how does the equation for V change? So again here, the tone or the sound depends on the frequency. So if it sounds a little flat, that's going to affect our frequency. So if it sounds flat, that's going to affect our frequency. It's going to decrease our frequency. So that means that our frequency would really have to be less than what it is now. And right now it's 80 pi. Remember that W variable, that constant, that was our frequency. So that 80 pi is representing our frequency. Okay, so that's basically the conclusion that they would want you to make there. Okay, so you might see a couple problems like that in your homework where they have you find the amplitude and the frequency and the period and graph it and then answer a few more questions about it. Okay, so we have 2 more examples to go through. And the next example is example 4, actually, and it's going to relate to these equations here. Now, all this is they've taken those equations that we had on the earlier slide, and they've just modified them a little bit. They've added a plus b at the end, so that means that we've got a shift where the graph is going to be moving up or down, so that's a vertical shift. And then they also have this t minus c in here. So that means that they're going to shift the graph either left or right. So those transformations that we saw in the sine and the cosine curves previously in the chapter can still happen in the real world. So these are just some pictures to model that. This is showing that we're taking our original sine curve and we're moving it up a value of b, and then we're moving it to the right a value of c. Okay, so that just shows the shift. And this is for the cosine curve. Okay, so let's take a look at example 4 here. It says a variable star is one whose brightness alternately increases and decreases. And for this given star, the time between the periods of maximum brightness is 5.4 days. So that means it has a period of brightness, and then it gets a little dim, and then it comes back up and it's bright again, and that takes 5.4 days to happen. And it says the average brightness or magnitude of the star is 4. And its brightness can vary as much as 0.35 more than that or 0.35 less than that in its magnitude. So for part A, it wants us to write an equation, but I'm actually going to draw a little graph. And the graph is actually what they want you to do for part B. Sketch the graph. Okay, so I'm going to start with part B here. And let me just make a rough sketch. And then I'm going to go back to the problem for just a moment. Okay, now it says that the average brightness of the star is 4. So let's just make that 4. That's my average brightness. That's kind of where I'm starting. Okay, and then it says that that can vary as much as 0.35. So I could go up to 4.35 or I could go down to 3.65 if I took 4 minus the 0.35. Okay, so the 0.35 is kind of like my amplitude. Okay, and then it also says that the time between the maximum brightness is 5.4 days. So they must have measured when the graph was really, really bright. So it would have been its brightest up here. And then it would have gotten a little bit dim and then gotten bright again. So the graph is taking this kind of behavior. And that amount of time would be 5.4. So this would be days. This would be our magnitude over here for our brightness. So this behavior looks like a cosine curve. So if I'm going to write my equation, it's helpful to draw a picture of what's happening first before you write your equation. So I'm going to be making an equation using this model right here, the cosine. Now we already talked about the amplitude, that was the 0.35. And I also need the, let's go back here then to where we're writing the equation. Let me write down that generic formula again. A cosine W t minus C plus B. Okay, so we already said that our amplitude is going to be the 0.35. Then I'll have my cosine. Now that brightness, our average brightness is 4. If you notice on my graph, usually the cosine curve starts up at 1. Okay, but here I'm not starting at 1. Okay, that average is kind of like the 4 there, and then I'm going above it and below it. So that 4 is actually going to be my B value at the end. That's how much I'm shifting the graph up. Okay, and then I have to find my frequency. I have to find that W. Okay, so that's going to be 2 pi divided by the frequency. And um, it takes me 5.4 days to go from brightest to brightest. So I'm going to take 2 pi and divide it by 5.4. Now remember, pi, we have a decimal for pi. So I can do this on the calculator. I can take 2 times pi and then divide it by 5.4, and I'll get 1.164 if I round. Now, the graph doesn't shift at all, left or right. I'm still starting on the y-axis like a traditional cosine graph does. So I don't have to worry about this shifting here at all. So that C value, there really isn't one. So if I'm going to write my finalized equation now, I think I have all the pieces. So y equals 0.35 times the cosine of, let's see, now I have a W. T is just going to be time, so I'm just going to leave that my variable t. And C I didn't have, so this would be like t minus C. I'm sorry, t minus 0, or just t. So my W is going to be the 1.164, but my t minus 0 is just going to be t. And then I'll have plus 4. I started up at 4. So for this type of a problem, or ones that are similar to it in your homework, I think it's better to do the graph first so you can kind of sketch out what's happening. You can see if you need to use the sine or the cosine model, and then fill in all the little pieces of information, all those little variables into the equation. Okay? And there's a prettier book graph than the one I drew. Okay, last example then is another type of simple harmonic motion. And this occurs when you have alternating current generators or AC generators. And alternating current is produced when an armature rotates around its axis in a magnetic field. So you take this piece of wire and you put it in this magnetic field and you rotate it around. So this is what's being modeled by this equation here. Okay? So as they take that wire and they pass it through the magnetic field, a voltage E is generated in the wire. And it can be shown by this equation. So this is another specific type of equation that we're going to use for this example coming up. And it says E sub O is the maximum voltage, and the W divided by 2 pi is the number of revolutions per second. Okay, so that's our frequency. So we're going to leave T alone. We're going to leave T as T for time. And then the E of T will be the voltage. So here, let's say that we have an ordinary 110 volt household alternating current, varies from 155 volts to negative 155 volts with a frequency of 60 hertz or cycles per second. So we're going to write an equation that describes this variation. So again, we're going to use this equation, E sub 0 cosine WT. Now we're going to leave T as T, so technically this is E of T. So we're going to leave T, we're going to leave the cosine. So we need to figure out the E sub 0, okay? And again, that was our maximum voltage. And then this W here, that was really the W divided by 2 pi. Okay, that was our frequency, our revolutions per second. Okay, so they told us our maximum voltage, our standard 110 volt, has a maximum of 155. So we'll just substitute 155 in there for the E sub 0. Okay, but I got to figure out that W part. Okay. Now they don't really tell me what the W is, but they do tell me the frequency. They tell me that if they take whatever W is and divide it by 2 pi, they get 60. So I have to work backwards here a little bit. W over 2 pi is equal to 60. So then if I solve this, if I multiply both sides by the 2 pi, I would have 60 times 2 pi, which is going to be 120 pi. So that's my value for the W that I'm going to substitute in here. So I'll have the cosine of 120 pi times t. So there's my final equation. So when you're doing these practice problems, definitely take a look at the book. All of these formulas are in the little blue charts in your book, so you might need to flip back into the actual section and take a look at them. They'll explain what all the parts are. Find examples in the homework that are similar to the ones in our notes, or there's other examples in the book as well, and use them as a guide. But remember, you want to sometimes draw a graph and see if it's a sine function or if it's a cosine function, and that will tell you which equation to use, unless they give you a very specific equation like our last couple examples. So remember that the binder in the classroom has all these problems worked out. They're odds though, so you can check answers in the back of the book. And if you have questions, come on in and see me before school.